Hello, everybody. Welcome to Nano at Tech. This is the periodic seminar series, monthly seminar series sponsored by the Institute for Electronics and Nanotechnology at Georgia Tech, as well as the Southeastern Nanotechnology Infrastructure Corridor, which is a member site of the National Nanotechnology Coordinated Infrastructure, NNCI, funded by the National Science Foundation. So this is our final spring 2021 webinar, and we are hoping, keeping our fingers crossed, to be in person starting in the fall in August, back in the Marcus building on the Georgia Tech campus, and we'll be moving back to 2 seminars per month at that point. We'll continue to have live streaming, so for those of you who are not close to the Georgia Tech campus, you'll still be able to log in and view the seminars that we offer in the fall. Before I introduce today's speaker, just a couple of announcements about some other upcoming events online. Starting in May, on Wednesdays, every Wednesday in May, from 11 a.m. to 12 noon Eastern Time, IEN will be offering its NanoFans program. NanoFans stands for Nanotechnology focused on nano biosystems. And this is a weekly seminar whose the theme for this semester for the May 2021 offering will be nanotechnology and vaccine delivery. And you can see more information about that on the IEN website. In addition, May 5th, also the first Wednesday in May, from 4 to 5 Eastern Time, we will be offering the first NNCI webinar. And this will be a computation webinar featuring Professor Dragica Vasileska from Arizona State University. And we hope to be offering NNCI webinars every month from now on. And again, you can find this information currently on the IEN website, and it will soon be on the NNCI website as well. So it's a real pleasure to have with us today Professor Andrew Cleland, University of Chicago. Andrew got his bachelor's degree in engineering physics and his PhD in physics from the University of California, Berkeley, and then just moved a little bit down the coast to the University of California, Santa Barbara, where he was professor there and associate director of the California Nanosystems Institute, before moving to the University of Chicago, where he is currently the John A. McLean Senior Professor for Quantum Engineering Innovation in the Pritzker School of Molecular Engineering. He's also director of the Pritzker Nanofabrication Facility and a senior scientist at Argonne National Lab. And also he is the co-director of the Soft and Hybrid Nanotechnology Experimental Resource, or SHINE, which is another member site of the National Nanotechnology Coordinated Infrastructure, NNCI. Andrew is a fellow of AAAS and the American Physical Society, and in 2010, Science magazine named work that he was doing as the breakthrough of the year. That's quite a high honor. So it's a real pleasure to have Andrew with us today to talk about quantum MEMS.
Okay, hopefully everybody can hear me. Thank you very much for the introduction, David, and also to Oliver for inviting me here. I'm going to share my screen now, so hopefully this will work. So the title of my talk is Microelectromechanical Systems in the Quantum Regime. This is a talk that I gave at the IEEE MEMS a couple months ago, and I modified it slightly for this venue. But it's basically exploring MEMS systems in the quantum regime, and I'm going to try to explain to you how we do that and what we've done that's kind of interesting in this regime. So your first question might be, why would you want to do this? Well, one is that MEMS systems are key to doing sensing of forces. And if you can operate them in the quantum limit, then in principle, you should be able to sense forces in the quantum limit, which is something that's quite difficult to do. So that's one key area that we're trying to go towards. Another is that mechanical strain and stress couples to almost every solid state quantum system there is out there, so that if we can control strain and stress in solids, then we might be able to link quantum systems together. So I've listed a few examples here of systems you might be able to link to. So superconducting qubits, which I'm going to talk quite a bit about because that's my other area, could then be linked to things called color centers, and you've probably heard of these as two-level systems in diamond, where they're called NV centers or silicon vacancy centers, and also in silicon carbide. There's also, you can link electronic devices to optics using optomechanical transducers. And there's a potential for linking to atomic qubits, so actually free atoms that people have figured out how to couple to nanoscale mechanical systems. And then a really interesting area, which has not yet been completely developed, is in quantum memory. So quantum memories are, there are a few systems that provide excellent quantum memories, but not good quantum computational facility. And there are other systems that have really good quantum computational facility, but don't have good quantum memories. And mechanical systems, it turns out, provide a really interesting opportunity in that you can make extremely high quality factor mechanical systems, and I've listed a few examples here at different frequencies, and their corresponding quantum memory lifetimes, so which range from tens of milliseconds up to a minute. And so these are really excellent for storage of quantum information. Now, all of these examples have not been demonstrated in the quantum limit yet, so that's an ongoing effort, but they do show the potential for really long-lived quantum memories. So this approach, basically mechanical quantum memories, may prove to be a really superior approach. So that's another really interesting area. So let me try to explain how you get a mechanical system in the quantum regime, and let me do that by talking about a really simple mechanical system, which is a mass on the end of a spring. So this is something people study in freshman physics or freshman mechanical engineering. This, of course, has a single resonance frequency given by the square root of the spring constant divided by the mass. And if you look, for instance, at the energy of the system as a function of how far you've displaced this mass from its rest point, the energy scales quadratically with the displacement as sketched here. So if you pull the mass out away from its rest point and then you let it go, it will oscillate back and forth about this rest point 0 at the resonance frequency of this harmonic oscillator. Now, if you take this system and you solve it in the quantum limit, which is something you do in first-year quantum mechanics, this is what are called the eigenenergy solutions look like. You have a ground state for the mechanical system, or for any harmonic system that's has an energy that's given by 1/2 h bar, which is Planck's constant, times the frequency omega. And then you have a series of energy levels spaced exactly by Planck's constant times the frequency, one above the other. This is a characteristic harmonic oscillator quantum mechanical solution. So if you want to operate a quantum system that has this energy spectrum in its quantum ground state, the biggest challenge is that you have to reduce the available thermal energy from the environment, which has an energy scale of kB, this is Boltzmann's constant, times the temperature in Kelvin. And what you need is that energy, kT, so that's sort of schematically shown here, to be much less than the spacing of these energy levels so that you can cool the system down into its quantum ground state. So to do that, you need Boltzmann's constant times the temperature to be much less than Planck's constant times the frequency. So what does this mean in practical terms? If you built a tuning fork resonator with a resonance frequency of, say, 1 kilohertz, then you would need to cool the system down to well below 10 nanokelvin. So that's 10 billionths of a degree above absolute zero. And no one has cooled a physical system to a temperature of this size, much less to temperatures much less than that. So this is an extremely difficult thing to do. There are people that are trying basically to do this, but without much success so far. However, if you relax this frequency and you try to operate at higher frequencies, then you can make this temperature requirement much less stringent. And so, for instance, if you're willing to work with mechanical systems in the microwave band, so here I've chosen 10 gigahertz, then to get this inequality to cool to the quantum ground state, you only need temperatures less than about 1/10 of a Kelvin. Now, this may still seem like at a really, really low temperature if you're used to working at room temperature, but it turns out this is not so hard to do. you can purchase, they're not cheap, but you can purchase a cryogenic system that's a turnkey system. You just need to plug it into the wall, and it will cool to temperatures of about 10 millikelvin, so 1/10 this temperature. So it's not so hard to get to this ground state operation requirement if you're willing to work in the microwave band. However, even if you can cool your mechanical system down to its quantum ground state, you need a way to measure what it's doing. And doing measurements on quantum systems is notoriously difficult. So you need a way both to measure the system and to control it at the quantum level. So how do you do that, assuming you've met this first requirement? Well, the easiest way to do that is to use another quantum system as your measurement and control system. So I'm going to describe to you how we have done this over the past, basically, decade. So the key to doing this is to use something called a superconducting qubit. So superconducting qubits are one of the hardware approaches to trying to build systems for doing quantum computation, quantum communication, and quantum sensing. And I'm showing here a bunch of pictures of experiments that I was involved in with a brief, like, 2-line description of what that achievement was over the past, 15 years or so. And these are the references to those different achievements. So these are superconducting qubits. And as I will show you, these are very simple to understand, and they're actually quite easy to fabricate and use in the quantum limit. As a result, because of the ease of fabricating these devices, they're quite high performance. They're easy lithographic processing. These are known as scalable. These systems have been very, very popular in the commercial sector. And so there's a number of companies that are using superconducting qubits to try to build a quantum computer. The first company to really get into this was IBM. They have quite a large effort. Google has quite a large effort and has made a lot of headlines recently. Intel has a smaller effort in superconducting qubits, a much bigger one on semiconducting ones. Amazon has a superconducting qubit effort. Alibaba in China. Rigetti is a small spinoff. The CEO of Rigetti came out of IBM. They're now based in Berkeley. Quantum Circuits is a spinoff out of Yale. And there's a whole bunch of other companies that are pursuing superconducting qubits for quantum computation. In addition to doing quantum computation, there's a bunch of other applications for these devices. So sensing is the one I'm going to be talking about. Also for just benchmarking different theoretical quantum protocols, trying to build hybrid systems, so coupling superconducting qubits to other systems for various reasons. Transduction, such as converting between microwave frequencies, which is where these devices work, and optical frequencies, and so on. So how does a superconducting qubit work? Well, a superconducting qubit is based on sort of the simplest electrical system, electrical circuit you can think of, which is the analog to the mechanical simple harmonic oscillator. It's an LC resonator. Okay. This has a single resonance frequency given by 1 over the square root of the inductance times the capacitance. And just like the mechanical system, you can easily build this to operate in the microwave band, but then quantum control and quantum measurement is challenging. Okay? What you do in order to make this much easier to operate in the quantum limit is you replace the inductor by a device that's given to us by superconductivity. This is a device known as a Josephson junction, and this is the electrical symbol for the Josephson junction. And this is what a Josephson junction looks like. We typically build our circuits using the metal aluminum. Aluminum becomes a superconductor below a temperature of 1 Kelvin, so it's a low temperature superconductor. And this is what a Josephson junction made of aluminum looks like. So we have 2 pieces of aluminum here, this sort of triangular shaped piece and this rectangular shaped piece, and they are in contact with one another over an area of a couple hundred nanometers on a side through a very thin tunnel barrier, which is made with the native oxide of aluminum. This barrier is very thin. It's thin enough that electrons, when the aluminum is in the normal state, can tunnel from one piece of aluminum to the other. And when the aluminum is superconducting, so below a temperature of 1 Kelvin, you get the charge carriers in the superconducting state, which are known as Cooper pairs, to tunnel through this. Now, the details of how this device works are really interesting. and there are many books written, and it does take a book to describe all the physics. But for the sake of this discussion, all you have to think about is this Josephson junction is just an inductor. So it replaced an inductor. It is still an inductor. But what's unique about it is extremely nonlinear, meaning its inductance changes dramatically as you change the amount of current flowing through it. Now, normally this would be a bad thing, but for operating in the quantum limit, it's what makes this device so great, okay? So you can write down the inductance of a Josephson junction. This is the expression for that inductance. This is, again, Planck's constant, so you know this is a quantum effect. This is twice the electron charge. This is the critical current of the device, which is measured in amperes, and typically for the devices we make is a fraction of a microampere. And this is the cosine of phi. Phi here is the phase difference of the macroscopic wave functions on opposite sides of this junction. So the wave function for the Cooper pairs here, which are all in condensed state, and the Cooper pairs here. So the details of this don't really matter. This is what the inductance is, and it's actually quite large. For a typical junction, we're talking about inductances of up to about a nanohenry, which is huge for a nanoscale device, okay? Now we can write down the Hamiltonian, or in other words, the energy for this electrical circuit. It has two parts. One is the charging energy of this capacitor. That's just the charge squared over twice the capacitance. And the other is the essentially inductive energy of the Josephson junction, which looks like this. If you then plot the energy as a function of the phase of the superconducting wave function, instead of having a parabolic shape, which is what the equivalent is for just a linear inductor, you get this cosinusoidal shaped energy as a function of phase. And it's replacing that quadratic dependence, which you have at small phases, but with this cosine dependence that makes this device quantum mechanical. So if you solve Schrodinger's equation for this system, the energy levels that you get, instead of being evenly spaced as you do for just an LC oscillator, they become anharmonic. So the difference in energy, or the frequency splitting between the lowest level and the first level, is given by one frequency. And then the splitting between that level and the next level higher is given by a different frequency. I've exaggerated the difference in the frequencies. They actually only differ by a few percent, but that difference is the key to making this a quantum device. So when we use this device as a qubit, we use the lowest two energy levels, the ground state and the first excited state, and we design these circuits so that the splitting energy here, or in other words, the frequency, is in the microwave band, so a few gigahertz. So when we cool this to a temperature of 10 millidegrees, this will be in its quantum ground state. Now, the anharmonicity means that if we put one quantum of energy in this circuit, so one microwave photon, and we trap it in this circuit, the energy to put another photon in is different. So if you drive this with a classical microwave source, you will not drive this up in energy the way you would if it were harmonic. Instead, you will just oscillate between these two levels. And that's what's give us quantum control over this system. This is what one of these devices looks like. They're lithographically patterned. This image is a couple hundred microns on a side. It's taken with an optical micrograph. And all the sort of silver colored material here is aluminum, which remember goes superconducting at 1 Kelvin. Everywhere that you see black lines, that's where we've cut through the aluminum and you're seeing the substrate underneath, which is either high purity silicon or it's sapphire. The qubit itself is down in the bottom slight right here. This cross-shaped structure is the capacitance C in our LC oscillator. And the Josephson junction, we actually use two in what's called a squid configuration, are down at the bottom of this cross. And here I'll zoom in with a higher magnification image here. Here's the bottom of the cross coming down. The two Josephson junctions are just right here and right here. And they are arranged in what's called a squid geometry, which allows us to tune the critical current of the junction and thus tune the inductance by just coupling magnetic flux into this loop that's outlined in yellow. So this is now a tunable LC oscillator, which we can tune over a frequency of a couple gigahertz when it's operating at a few gigahertz. Okay, there's a bunch of other elements in this picture. So one is this line right here, which is just a flux coupling line. So if you drive a DC current through this wire and it connects to ground here, that will inject flux into the squid, and that's how we tune the frequency of our qubit. We have another line that comes in from the left here. That's where we put in microwave signals to excite the qubit and to control its phase. So this line is used to control the quantum state of the qubit. And then finally, we have this structure right here. This is a quarter wave microwave resonator, just a classical microwave resonator. It's a coplanar device. It's shorted at this end to ground, and at this end, it has a capacitive coupling to the qubit. We measure the frequency of this resonator by sending weak microwave signals through this transmission line right here, allowing us to monitor, by injecting a small amount of energy in this resonator, what its resonance frequency is as it is loaded, electrically loaded by the qubit. So the qubit, when it's in its ground state, will pull the frequency of this resonator by some amount because it's capacitively coupled. And when the qubit is in its excited state, it will pull the frequency of this resonator by a different amount. And by measuring that resonance frequency, we can actually measure the state of the qubit. So that's how we do quantum measurement of this device. And quantum control is afforded by using this microwave coupled line and this DC line. The last part of the cross allows us to couple this qubit to other qubits or to mechanics, as you'll see. These are made in our clean room at the University of Chicago. This is a new clean room. It opened for business in 2016. All the tools are brand new. Here's a picture from the outside. We have floor to ceiling glass windows. This area is not clean, so visitors can come in and look inside, and you can see some people working in here. And this is a list of all the equipment we have. We have plenty of equipment to do a huge range of things, including making quantum devices of various types. To cryogenically cool our qubits so that they operate in the quantum ground state, we use this piece of equipment right here. This is a dilution refrigerator, and everything on this plate and below goes to a temperature of about 10 millikelvin. And you can see all the microwave cabling on here, as well as cabling on the higher temperature stages up here. At room temperature, we have custom electronics to both control and read out the qubit state. Here's a rack of some of the electronics. This is enough electronics to control about 5 qubits. And we also buy some commercial equipment for microwave characterization. So we first were able to use a superconducting qubit to control a mechanical device. And I'm just going to very quickly show this. In 2010, so this was about 10 years ago, this is what this science breakthrough of the year was attributed to. And this was, we had a superconducting qubit on this integrated device coupled to a microwave bulk acoustic resonator with a resonance frequency of 6 gigahertz. Here's the bulk acoustic resonator, and it doesn't operate in a sort of diving board motion. Instead, it's a dilatational mode where the thickness of this suspended structure changes at a frequency of 6 gigahertz resonantly. And it's piezoelectric, so that gives us an electrical coupling signal to the qubit. And I'm not going to explain in detail how this worked, but we were able to measure that this mechanical system was cooled to its quantum ground state, and we were able to measure by interacting the qubit with the mechanics what are called Rabi oscillations, which are a demonstration that you're exchanging one quantum of energy between the qubit and the mechanics, meaning that you're transforming a photon in the qubit, a microwave photon, into a microwave phonon, which is the quantum of mechanical vibration. So basically you have this harmonic oscillator at 6 gigahertz with these energy levels, which for this 6 gigahertz frequency are spaced by about 0.3 Kelvin, and we cool it to about 20 millikelvin in this particular experiment into its quantum ground state. And then, like I said, we can measure these Rabi oscillations where we are creating a photon in the qubit here, and then swapping it into the resonator here, and then getting it back into the qubit. And this is what's called a Rabi oscillation with, in this experiment, a very short lifetime of just a few nanoseconds, because it was a terrible very low Q resonator. And the low quality factor of this resonator, the fact that the energy dissipated so quickly, limited what we could do in this experiment. And it took us basically 6 or 7 years to figure out how to improve on this device. And this was by going to, instead of a bulk acoustic resonator, going to a surface acoustic wave resonator, which I'm going to describe here. So surface acoustic waves are excitations that you can generate on the surface of a piezoelectric substrate by using these kind of interdigitated transducers that you apply an oscillating voltage to alternating fingers. The spacing of the fingers corresponds to the wavelength of the surface acoustic wave, and you have to set the frequency of your excitation voltage to match the corresponding frequency of that wave. And you can send an electrical signal into a transmitting IDT. This will then send a surface acoustic wave, which you can then catch with a receiving IDT. And you can design and operate these devices over a wide range of frequencies. They're very compact, very small, very tailorable, and operate at very low powers. And they use mostly the fact that phonons, so these surface acoustic wave quanta, travel 100,000 times slower than photons, so that one of the prime uses for these devices is delay lines when you want to slow down an electrical signal. But you can also use them for doing pulse shaping and pulse compression. You can build room temperature resonators that work really well, much better than their purely electrical analogs and so on. And so the question was kind of, can you use surface acoustic waves in the quantum limit where you're dealing with single phonons? Can you build qubits out of these and send them from one place to another, and so on? So we started exploring these, and this is an example of one of the key experiments we did prior to going into the quantum limit. This is a surface acoustic wave resonator fabricated on a very strong piezoelectric lithium niobate. And this consists of a transducer in the middle right here that can emit and receive phonons, and then mirrors, which are just lines spaced by the wavelength of the surface acoustic wave that we are generating on either side. And this is all designed to work at a center frequency of 4 gigahertz. And if you zoom in on these mirrors, they are just, like I said, fingers of metal. Each one reflects a small part of a wave that's incident on it, and a whole bunch of them together acts like a phased array mirror. So you measure these at cryogenic temperatures. These are at 10 millikelvin. But using a classical equipment, a vector network analyzer, to send the signal from this pad through the transducer to this pad, and you measure the transmission of the signal as a function of frequency. This is the magnitude as a function of frequency. You can see the scale here is in the gigahertz band. And then this is the phase. And so you get this kind of response shown in black and red. And I fit a embedding circuit, so the stray, inductance, and capacitance, by these blue lines right here. Then what we do is we add to this embedding circuit a 4-parameter model that's built from standard piezoelectric theory in order to fit the 4 parameters and see if we can match this measured response with the model response. And you see that we can get very good agreement between the model and the experiment, and then we understand what all the features are in this structure. So basically, each one of these resonances is Fabry-Perot mode for this acoustic Fabry-Perot resonator. The width and depth of this resonance allows us to extract the quality factor for that resonance, and for these resonances, they were around 20,000 at 10 millikelvin with 1 phonon of energy. And the free spectral range, the spacing between these resonances, is about 6 megahertz, which is what we expect from the spacing of these 2 mirrors. And we really understand all the details. The reason these resonances are strong over this range of frequencies and then fall off is because the mirrors have a limited range of frequencies over which they work well. So once we're over on these edges here, that's where the mirrors are not working well anymore. So that's the mirror stop band. Okay, so now that we can make this kind of acoustic resonator at 4 gigahertz with a quality factor of 20,000, we wanted to couple this to one of our superconducting qubits. And in order to do this, we first changed the acoustic resonator design by moving the mirrors really close together so that you increase the Fabry-Perot free spectral range so much that we only have a single mode in this transducer in the mirror stop band. And that was so that the quantum experiments would be easy to understand. We then couple this to a superconducting qubit. Here's a ideogram for a superconducting qubit, which we couple to the transducer through an electrically controlled variable coupler so that we can turn the coupling between the qubit and the acoustic resonator on and off electrically, allowing us to do good analysis. This circuit is fabricated on a separate chip, a sapphire chip, from the acoustic resonator, which is fabricated on a lithium niobate chip. And then the two are combined by using a flip chip approach and using air gap inductive coupling between the signals on the sapphire chip and the lithium niobate. So we have no galvanic contact between these two chips. So here's a detail of the lithium niobate chip with its inductive coupling and its acoustic resonator, and the details for that. And here is the qubit circuit, so you should recognize this shape with its readout resonator, the qubit. This is our tunable coupler. I'm not going to explain how that works. And this is the inductive coupling to the lithium niobate chip. And then you take the lithium niobate chip, which is this black unit here, you flip it upside down, align it under a mask aligner to the sapphire chip, which is this chip right here. You can see the qubit right here. They're inductively coupled together, and all of our electrical contacts are made. You can see all these wire bonds to the qubit chip, and a lot of wire bonds for making a good ground. And then this is a sample mount that we use with microwave connectors on it. Okay, so now we cool this thing down, and we use the qubit to probe the resonator. And this is a measurement of the qubit loss when it's coupled to the acoustic resonator as a function of frequency. And you get this very complicated response that actually took us a while to figure out what it was, okay? But we see a very strong peak in the loss right here, and we see all these little resonances with this kind of overall asymmetric shape. So then we use the same 4-parameter model to try to fit the acoustic resonator to this measurement. And here is a fit of that same 4-parameter model that we understood the classical measured device earlier. Here plotting what the model admittance is as a function of frequency. Using just 4 fit parameters, you see we get a very good agreement between the admittance and the qubit loss, with the central peak here, the overall asymmetric shape, and all of these wiggles. There's a couple things we don't understand. These things right here are not understood. And there's some mismatches between these, but you have to say the agreement is quite good. From the model, we now understand what everything is. The mirror stop band is this range right here, okay? This resonance right here is the single Fabry-Perot resonance that we have trapped in the mirror stop band. So that's the mode that we're trying to talk to. The asymmetry is because our transducer was not designed exactly correctly. Its resonance frequency should have been here, but we missed slightly by a couple hundred megahertz. And that's why you get this asymmetry. And all these ripples are just the ripples in the mirror response, similar to those that we saw in the larger device. Okay, now that we understand what's going on, we can now start to play with this surface acoustic wave mode, which is the one we're interested in. So here's a sequence of plots where I'm changing the coupling between the qubit and the acoustic resonator. So here there's zero coupling, here there's maximum coupling. And I'm driving the qubit with a weak microwave tone whose frequency is set along the vertical axis. And along the horizontal axis, I'm tuning the qubit, so through the acoustic resonance. With no coupling, you don't see any structure at all. This is exactly what we expect. By the way, the color scale here is that we're measuring the qubit in the excited state, meaning that this microwave frequency matches the qubit frequency set this way. Then as we turn the coupling up, you get what's called an avoided level crossing in the response of the qubit. This is exactly what you expect when a qubit is tuned through resonance with a harmonic oscillator, which is what this one mode in our structure is. And at the maximum coupling of 7 megahertz, we can fit this very well to just a very simple two-level system coupled to a harmonic oscillator, where this is the harmonic oscillator frequency. That is our surface acoustic wave mode at the design frequency as we got from the prior measurement. Now what we can do is we can do some time domain measurements to generate a phonon by using the qubit as a phonon generator, turning on the coupling, and then watching the qubit and the resonator interact. So these are these Rabi oscillations that I had shown you on the experiment that we did 10 years before this one. The vertical scale here is the interaction time between the qubit and the resonator. The horizontal scale is the tuning of the qubit with respect to the surface acoustic wave mode. This is where it's exactly on resonance. And the color scale is the probability that the qubit is measured in its excited state. So if we just look along this line right here, we see that the qubit starts in its excited state. It goes to its ground state. This is where we have one phonon in the resonator. The qubit then gets re-excited. No phonons in the resonator. Then we swap the phonon back into the resonator, and it will just oscillate with a time that's given by the combination of the qubit lifetime and the resonator lifetime. We also
Andrew, just 15-minute warning, okay?
Thank you. So we can also generate quantum states in the resonator using the qubit. So here are 3 different quantum states in the resonator. This is the quantum ground state, and we measure this using a technique called Wigner tomography, which is kind of a snapshot of the quantum state in the resonator. And the top set of panels is experiment, the bottom set is theory. So this is the ground state, very good agreement. This is where we have one phonon in that surface acoustic wave mode, and you get this very classic shape with a negative valued Wigner tomogram in the center, and that negative value is sort of the holy grail, surrounded by a positive valued donut, again, good agreement. And then if we do a superposition state of where the resonator both has no phonons and one phonon at the same time, you get this double-lobed positive valued tomogram on the right, negative valued on the left. Again, very good agreement between experiment and theory, showing that we have full quantum control over these acoustic quantum states. All right, now I'm going to very quickly go through another experiment we did, which is where we went back to the long acoustic resonator. Here it's 2 millimeters long, with a transducer in the middle and mirrors 1 millimeter away on either side of that transducer. Again, designed to work at 4 gigahertz and now with a free spectral range of 1 megahertz. And it takes half a microsecond for a phonon to be launched from this transducer, go to the mirrors on either side, and then come back and interact with the transducer again. This is fabricated on a lithium niobate chip. And then we're going to couple 2 superconducting qubits fabricated on a single sapphire chip, but of course different from the lithium niobate chip, each qubit having a variable coupler allowing us to turn its interaction with the acoustic resonator on and off. So now what we do is we test this device using one of the 2 qubits, and we excite the qubit, turn the coupler between the qubit and that long acoustic resonator on, and then wait and watch what happens. So, and we measure the qubit state. This is a color scale, again, where red means the qubit is measured in its excited state, blue means it's measured in its ground state. The vertical scale here is the qubit frequency. The horizontal scale is how long it's been interacting with the acoustic structure. And if we just focus on the middle part here where the qubit is tuned to the device, what you see is that the qubit starts excited, it very quickly decays to its ground state. And now we just wait, and the qubit stays in its ground state for a long time, half a microsecond, and then it's all of a sudden re-excited with a blip, okay? If we don't stop the experiment but continue, that blip goes away. We wait another half a microsecond, and the qubit gets re-excited. What's going on here is that the qubit launched a phonon. It took half a microsecond to bounce to the mirrors and reflect back, and then it's re-exciting the qubit. And if we don't stop the experiment there, that phonon continues and re-excites the qubit a second time. So this range of frequencies is the range over which the transducer that launches the phonons works, while this is the mirror stop band for the mirrors in that structure, and then this is a single bounce and a double bounce. We can then tune up how the qubit interacts with the resonator in order to improve the fidelity of that phonon emission, and that is shown here, where we're exciting the qubit right here. We're turning on the coupling much more gradually now to carefully emit a phonon. We then wait, and then we try to catch it with the qubit half a microsecond later. So that's shown here, where I'm plotting the probability of measuring the qubit in the excited state as a function of time. We start after exciting the qubit with the qubit in the excited state, we then very gradually release that phonon in a way that we have a symmetric phonon envelope as it travels through the device, and then we catch it half a microsecond later, and the fidelity of that capture, or in other words, the capture efficiency, is just under 70%. And we know from other measurements that the difference between this and 100% is phonon loss as it travels through the resonator and bounces off the mirrors. So the mirrors actually scatter some of the energy of that phonon into the bulk, and that's where we're losing most of the energy here. But this is quite good. Okay, then what we can do is we can actually build a single phonon interferometer. This is a really interesting experiment for doing solid state probing. So now what we're going to do is we're going to take the qubit and excite it, but then we're only going to release half a phonon into the resonator, meaning 50% of the time we release one, 50% of the time we don't, generating an entangled state between the qubit and the resonator. That's written here, qubit in the ground state with one phonon in the resonator, superposed with the qubit in the excited state and the no phonon in the resonator. We then change the phase of the qubit and then catch the phonon at the end, and this capture will depend on the phase of the qubit that we've injected electrically. And that allows us to build an interferometer where either when we release the half phonon, the qubit is now sitting here with the phonon traveling, we change the phase of the qubit here. So depending if we change the phase by 0 degrees, we will recapture that phonon, while if the phase is set to pi, the qubit will instead release its phonon. And from this final state, we know whether we got a constructive or a destructive interference at the qubit. And then we can plot that interferometry as a function of the phase, and you get this beautiful interferometry with large, highly visible fringes. And we are now doing experiments where we're trying to manipulate the phase of the phonon as it travels through the material. Finally, we can do a two-qubit state transfer where we send a phonon from one qubit to the other. That's shown here. So here we're using both qubits coupled to the resonator. We use qubit 1, we carefully launch a phonon into the resonator. Qubit 2 is also excited, and we sometime later launch its phonon into the resonator. So here we have 2 phonons in the resonator. Then we use qubit 2 to catch the phonon from qubit 1, and qubit 1 to catch the phonon from qubit 2, with these interactions carefully timed so that we have a half microsecond from qubit 1 sending and qubit 2 catching, and qubit 2 sending and qubit 1 catching. And you see that we get about the same efficiency for the recapture. If we instead do this with a half phonon, so qubit 1 simply emits a half phonon, qubit 2 does nothing, and then we catch that half phonon with qubit 2, then we can generate what's called a Bell state between the 2 qubits, where we have a superposition of qubit 1 being excited, qubit 2 being in the ground state, qubit 1 being in the ground state, qubit 2 being in the excited state. And the fidelity for generating this entangled state, which is a key to doing quantum computation and communication, is about 86%. So this is really good. And this shows that we can basically entangle qubits using a phonon as the intermediary. And this is the first time this has been done. So we have a bunch of other experiments, but I've run out of time. So just the outlook here is that we've now shown that we can quantum control acoustic vibrations, and we can quantum control itinerant phonons and send quantum information using those phonons. We're now trying to use this capability to explore quantum optics, but using phonons instead of photons, because there's a whole bunch of really interesting fundamental experiments that can be done. We're working on coupling superconducting qubits to other quantum systems using phonons. We're trying to use optomechanical devices to couple superconducting qubits to infrared light, so that then you could program a superconducting qubit by sending an optical signal and vice versa. And also, like I mentioned at the beginning, trying to use superconducting qubits to couple to mechanical memories, which is a capability that isn't available in superconducting qubits. So here's a picture of my group. This is pre-pandemic. It's the last time that we got together. Kevin Satzinger here was the guy who did the surface acoustic wave resonator experiment. He's now leading Google's 54-qubit quantum computation project in Santa Barbara. And Audrey Bienfait did the experiment with the 2 qubits coupled to the phonon launcher, and she's now on the faculty at the École Normale Supérieure in Lyon in France. And a bunch of other people, but I'm going to stop here. Thank you very much. I will take questions.
Great. Thanks very much, Andrew. That was really, really interesting. People should enter questions in the Q&A box, and I will read them out. Nothing yet.
Maybe I can start with a question.
Sure. Go ahead, Alan.
Andrew, you showed the nice fabrication facility at U Chicago. What are the fabrication challenges for these type of devices?
Yeah, that's a great question. So there's a bunch of different platforms that people are exploring for quantum applications. Like I said, superconducting qubits are kind of the favorite for most of the commercial ventures, but people have probably heard that there are sizable commercial efforts to try to develop ions as qubits. So Honeywell has very publicly made statements about what they're doing with their ion-based quantum computation. And there's also a spinoff out of University of Maryland, which got quite substantial venture capital money trying to build an ion-based quantum computer. So ions are, they're essentially perfect devices because they're atoms just missing one electron. But when you take an ion, you have to control it, and they are usually controlled using ions floating in vacuum, but closely coupled to a lithograph device. And what they find is that when those ions get close to the surface, they don't behave nearly as well as they do when they're really far away from anything physical. And so they have been developing methods to clean these structures that they use to control the ions and learning all about the solid state. Superconducting qubits have the same problem. Superconducting qubits are made out of superconducting metals, which are very good metals. Basically, you've gotten rid of all the normal metal electrons, so they can conduct electricity at microwave frequencies and all the way down to DC with no loss. However, these are fabricated on the surfaces of imperfect materials, just as ions are when they interact with the surfaces. The superconducting qubits will interact with dirt, or more precisely, two-level systems in the substrate. So it doesn't matter what substrate you use, there's always some dirt there. Some of those two-level systems are microwave active, some of them are microwave electrically active, and they will basically absorb energy from the qubits, reducing the qubit lifetime, reducing the fidelity of the qubits, and so on. So that's the number one problem in the performance of superconducting qubits, is that they interact with unwanted two-level systems. And these include, things that are sort of intrinsic to the material itself. However, it also includes things like oxygen has a small magnetic moment, and when oxygen is trapped on the surface in the form of water, which is very hard to avoid, that will also limit the performance of superconducting qubits. And then there's also just, the stupid effect, which is where you couple your superconducting qubit too strongly to an external measurement line or an external control line. But those are problems that you can engineer away. But I would say, yeah, the biggest challenges are getting rid of unwanted two-level systems in the surface of the materials that you fabricate on, in the surface of the aluminum. So aluminum tends to oxidize, and some of the oxide is not perfect aluminum oxide. Instead, it includes some, contaminant, things like oxygen, things like water or other contaminants, and getting rid of that is a big problem. So right now, the very, very best qubits that you can get have lifetimes of around 100 microseconds in terms of a repeatable device, and that is limited by things like two-level systems. The qubits that we make, the very best ones we've made, have lifetimes of about 50, 60 microseconds, so a bit less than the record. but more typically they're around 10 or 20 microseconds. And this is really just, how careful we were in producing those devices. In terms of how to clean these, it's not clear. There's no agreed upon recipe which if you do the following, your qubits will be better. And that's, I would say, is still under development. Thanks.
Great. We have questions. But Oliver, did you want to say something?
Nope, I'm good.
Okay. So we have a couple more questions. We'll see if we can get through a couple. So Walter Henderson asks, does the use of phonons as message carriers limit the potential computation speeds of this technology, or does the speed gain of superimposed entangled states for processing overcome that limitation by orders of magnitude?
Yeah, so that's a great question. So what I would say is that when people are interested in doing computation between, let's say, superconducting qubits, they're not going to use phonons. They're going to use photons. Photons travel at the speed of light, and when we build, 2-qubit gates or multi-qubit interactions, it's all done with microwave photons, because then you don't have to deal with the delay of the acoustic signal. So the acoustics, however, is important because it might enable you to couple a superconducting qubit to another system that it doesn't behave properly in the electromagnetic domain. And in particular, there are color centers in, for instance, diamond and silicon carbide, that they do interact with light quite well. But in terms of the microwave band, you need really, really strong microwave signals to affect those types of color centers. Unlike my superconducting qubits, which work with just, 1 or 2 microwave photons. So coupling a superconducting qubit to a color center electromagnetically is very hard to do, but it turns out that color centers are extremely sensitive to strain, and if you're using the right quantum level manifold, you can control a color center with a single phonon. No one's demonstrated that yet, but the numbers are all right. So I think really the application here is in hybrid quantum systems.
Great. Another question from Nathan Lee asks, what kinds of challenges arise for galvanic contact between the bottom chip and the top chip?
Yeah, so companies like Google and IBM and also Lincoln Labs have developed a flip chip technology that includes galvanic contacts. So they use chips that are fabricated with typically aluminum, possibly niobium as the superconducting metal. And then they have machines that will flip chip bond these together using indium, which is a very soft superconducting metal, to form the galvanic contacts, and they just crush the two substrates together to get a good electrical contact. And that's a very reliable technique. Both Lincoln Labs and Google and IBM have demonstrated, in refereed publications, that they can get really good galvanic contacts between superconducting qubit circuits made in that way. However, the equipment that it takes to do this, first of all, it costs about $1 million to keep a system. Second of all, you need a really experienced staff person to operate it. Pretty much, this is not a tool that, a graduate student with 6 months experience in a clean room is going to operate properly. So those are really hard to use, and that makes it kind of out of the reach, the price and the staffing requirement, kind of puts this out of reach of most academic groups. However, our technique uses just standard substrates. One of them has to be transparent, and just a standard contact aligner. We use a Carl Seuss MJB3 to do our contact alignment. And you don't need a galvanic contact because you have good inductive coupling for the signals and good capacitive coupling for the ground. So it turns out that you don't need a galvanic contact to get good electrical control, as long as your circuits are not too complicated. We have done circuits where we have superconducting qubits on the flipped over chip and superconducting qubits on the base chip, and we're only making wiring contacts to the base chip. And those work very, very well. There's no degradation in the performance of the qubit that's on the non-galvanically contacted substrate. We don't have a way to make galvanic contacts. That would require quite an investment. But so far we haven't needed it. So it's a great sort of inexpensive way to explore flip chip geometries without having to go to this very expensive approach.
So we are 5 minutes past the hour. I don't know how you are on time.
I'm fine. I'm fine.
Okay, so people, yeah. I'm gonna wrap it up. But if people want to stay on and listen to the answers to additional questions, I'm happy to stay on. And it sounds like Andrew's happy to stay on. So I'll keep asking the questions. But again, thank you very much for joining us today. We really appreciate it. So the next question is from Devin Brown, who asks, was the Dolan bridge shadow evaporation technique used for making the Josephson junction?
Yes. So there's two sort of popular methods for making Josephson junctions, and this is clearly somebody that knows what they're talking about. We do use the Dolan bridge technique. This was invented, I think, in the 1970s. Typically, there's a bunch of ways to do this, a bilayer of PMMA, which is an e-beam resist, and a copolymer of PMMA as a underlayer. And the underlayer is much more sensitive, so you get undercut when you expose and develop it. And you pattern it so that you have a bridge of PMMA that you then evaporate in two angles with an oxidation step in between to define the Josephson junction. That's probably the most popular method for making Josephson junctions. There's also a method that uses what's called a Manhattan technique, which allows you to make larger area devices, but we've stuck with the Dolan method because it's very reliable and makes quite good junctions.
Okay, here are two questions from Eric Woods. The first one is, do you see the potential for interacting qubits with IR, infrared, since you hinted that this would be possible with transparent substrates like sapphire and lithium niobate? And the second question is, if you create multiple mechanical memories on a chip, how scalable do you see that? For example, do you see that leaky?
Yeah, so I'll answer the second question first. So right now, the favorite memory in the superconducting hardware approach is to use either a coplanar waveguide resonator, and there the longest lifetimes you can get are maybe a few hundred microseconds. But if you go to a 3D machined microwave cavity, and the most popular ones are these quarter wave coplanar sub-resonators, there you can get lifetimes that are in the maybe 1 to 10 millisecond if you really work hard at it. However, the problem with those resonators, even though they are very long lifetime, is that they are gigantic. They are centimeter scale machine devices. And if you need a lot of them, it doesn't scale up well at all. So there's a huge challenge in making, a large scale multiplexed quantum memory using that approach. If you could make mechanical resonators with the equivalent or even higher quality factors, you could get the same lifetimes in the same frequency band, but the mechanical resonators are far, far smaller because the speed of sound is so small compared to the speed of light. So you can make really high quality factor, gigahertz frequency mechanical resonators that are just, they're contained in a volume that's maybe, a couple hundred cubic microns. So really small, very compatible with the size of the superconducting qubits. No one, however, has figured out how to make a really high quality factor mechanical resonator that integrates with a superconducting qubit. But there's a bunch of people trying to work on that. And in fact, I think this is one of the development goals for Amazon in their quantum computation effort. So that was the second question. Hopefully I answered that. The first question is related to this. So I think what you're asking is there a way to couple superconducting qubits to light and in particular infrared light? And there is a way to do this. This is using optomechanical transducers. So these are the same kind of mechanical structures that I just talked about for quantum memories, but where you add an optical cavity, which looks very similar to the mechanical cavity, and in fact the two are superposed and interact very strongly, generating what's called an optomechanical interaction. And people have shown that you can transduce between microwave mechanical frequencies and infrared telecom wavelengths. So when you go from microwaves to optics, you generate side bands on the optical signal, add a microwave band offset from the main carrier signal, and you can go the other way where you put a modulated optical signal and drive the mechanics. And then the challenge is, can you go both ways and integrate a superconducting qubit? We've had an effort, we've been working on this for 7 or 8 years, and we're very close to being able to show a bi-directional quantum level operation of such a device. We have plenty of competition. I would say that the group that's actually furthest along is Oscar Painter's group at Caltech, where they've shown one-way quantum operation, but they haven't shown the reverse direction. So they've gone from microwaves to a modulated optical signal, but not the other way around yet. But they're working on that. And I think this is going to happen in the near future, where you'll basically be able to program a superconducting qubit with a telecom wavelength optical signal and use the superconducting qubit to generate a modulated quantum level telecom signal, which could then be used for quantum communication and, in principle, build a quantum repeater. There's other approaches to building quantum repeaters as well, and there I would point you to the Yale groups of Hong Tang and Michel Devereux that have made really spectacular advances.
Great, and I think our last question is from Stephen Schwartz, who asks, are there large losses in coupling efficiency due to the inductive coupler, and are these losses greater than the losses due to the fabrication?
So no, we've had very good performance for all of the electrical circuitry associated with these devices, so we really don't have much loss in the inductive coupler. I mean, it's all superconducting metal. They're not resonant, and the substrates are not lossy for the magnetic signals that we're talking about. All of the losses in our devices come from the acoustics. So there's a small amount of loss in the transducers, and there's a lot more loss in the mirrors. And this is a problem that's well known for mirror structures built on lithium niobate. The lithium niobate is such a strong piezoelectric that you get mode conversion between the surface acoustic wave signal and bulk phonons. So basically what happens is that the surface acoustic wave signal hits the mirror, and most of it is reflected back in the surface acoustic wave channel, but some of it is transmitted instead into the bulk. So it basically scatters off the mirror into the bulk, and then those are gone. And we believe that that's the primary loss mechanism in our devices. There's probably some electrical loss, but it's at the few percent level compared to, what I was showing for these acoustic devices, where we have, 20, 30% for this 2 millimeter long throw acoustic resonator.
Great. Well, thank you for staying on an extra length of time to answer all the questions. We appreciate that. And I think we will finish up and say goodbye to everybody and see you at the next webinar. Great. Very much.
Thank you very much for the invitation. And thanks for the audience for sticking around. Cheers.
Bye.